Hi, I'm Alex,
And I'm Johnny.
and today we'll be talking about how machine learning models can learn context based emotional nuances from uncontextualized labels. So, the task of text based emotion classification is to infer the writer's emotion from a given text. And here is an example where we would want to label the sentence with sadness because they started crying. And the general pipeline for this machine learning task is you start with the text as input, which can be like a sentence or a conversation to provide context. This text is then processed through tokenization and embeddings to be represented in vector form as a bunch of numbers. You can then use RNNs or transformer-based models to predict a final classification. In effective computing, emotions are typically classified based on one of the dominant emotional models, such as Ekman's basic emotions. As you can imagine, this would have applications in customer feedback analysis and healthcare.
Transformers are a state-of-the-art family of language model that uses self-attention mechanism, allowing it to capture long-range dependencies, achieve parallelization, and understand context. These models come as encoders or decoders, generally used for classification and autoregressive generation, respectively. However, limitations can arise from its large size and computational inefficiencies, namely its quadratic time complexity.
One critically underrepresented aspect of text based emotion classification is the importance of context. Without context, it is easy, even for humans, to misinterpret phrases such as this for sadness, when adding context can give it an entirely new meaning. In this case, context shows that the user is crying from joy, not sadness.
Several works have been conducted in this area, including contextual datasets and context-aware models. Contextual datasets such as emotion lines, meld, and emo context provide the conversation as input to give contextual information. However, there are few contextualized datasets, making them difficult for practical use. Context-aware models are models trained on contextualized datasets and receive conversations as input. Many of these models, such as ANA and EmoXQ, are BERT-based models, which have been shown to be effective.
So, in this project, we propose a novel method to train a context aware model from uncontextualized datasets, foregoing the need for contextualized datasets, avoiding the aforementioned problems, and saving the need for manual annotation.
Our experimental setup to evaluate our method is as follows. First, we train a context-aware control model provided with labeled contextualized data. The blue L here representing the ground truth label. This control model represents the ideal scenario and an upper bound to our method's expected performance, where we have access to a contextualized dataset that fits our task. A context-blind control model is also trained with uncontextualized dataset, representing the lower bound or starting point of our method's expected performance where the model is completely ignorant of context. Our model starts with the same uncontextualized dataset, but trains a context-aware model through a special training procedure and the addition of an unlabeled context dataset. This is just a raw conversation dataset that can be easily scraped from any desired source like social media.
To carry out our experiments, we use the emotion lines dataset, which is a contextual dataset. We derive all other forms of data from the same dataset so that they all use the same training data for a fair comparison. To obtain the contextualized data, no change was necessary. Uncontextualized data is created simply by removing all utterances except for the target utterance from each conversation. And unlabeled context is easily obtained by just removing the labels of each conversation. When measuring performance, we use the unweighted accuracy metric, which weighs each class equally regardless of support, as shown in Figure 6.
Our method, context infusion or COIN, starts by training a context-blind helper model on the uncontextualized input, much like the context-blind control model. Next, we use this helper model to generate the labels of each final utterance in the unlabeled conversation dataset, denoted by the purple L. This creates a noisy labeled contextualized dataset.
We can then use this noisily labeled contextualized data to train a context-aware target model, much like the context-aware control model. Now, these noisy labels are not just noisy in the conventional sense as they are generated, but they are noisy as they may not reflect the accurate emotion given the situational context, because they are generated from a context-blind model. Training on these context-blind labels can lead to unwanted context-blind behavior in our target model. Potential symptoms that would indicate that our model is still behaving like a context-blind model are 1. The model does not understand the context and thus has the same accuracy as a context-blind model, and 2. The model never uses context, so changes in context do not affect its output. Ideally, having context in its input offers enough additional information for the model to overcome these problems. But with no additional changes, the optimal behavior for the target model is still to become an identical copy of the helper model that generated these labels. To combat this, we apply a masking strategy during training, which masks out the final utterance with a probability of alpha. This essentially forces the model to use the context to make a prediction. We have provided the implementation details here if you want to pause and take a look.
So after evaluating our models, we found that the target model does perform better than the context-blind control model, and this refutes the potential symptom mentioned earlier that the coin model will exhibit context-blind accuracy. This performance discrepancy is evidence that the target model is utilizing context during prediction, and despite seeming small, a 1% performance gain aligns with prior findings of Aporia and others who reported a similar 1–2% improvements due to context. Here, we demonstrate the target model's context-aware capability in a conversation. Figure 10 shows two example conversations, both ending with great, but the model correctly recognizes the sarcasm in the second example from using context. This refutes the other potential symptom that the coin model will not adapt to changes in context.
In figures 11 and 12, we shift gears a little to extend our methodology to train a coin model with a masking probability of 100%. This changes the nature of the task from simply classifying emotions to predicting them from past context without actually using the last utterance. Figure 11 shows the accuracy of this model. A low accuracy is expected given the difficulty of the task, but it still outperforms a random baseline by more than 2 times. Interestingly, figure 12 suggests that the model performs much better on specific emotions, such as anger, which doesn't necessarily correspond to the number of training samples the emotion has. This suggests that certain emotions are intrinsically easier to recognize from context than others.
In conclusion, the coin method is a simple and scalable method to train context-aware models for uncontextualized labels, and our results support the effectiveness of the proposed coin method. By using 100% masking probability, we introduce a new task to predict future emotional responses for solely past context. We also show that certain emotions may be intrinsically easier to recognize than others, and we would like to see more work in this direction.
We would also like to explore including other modalities such as video and audio to coin, applying coin to other tasks, and expanding the coin alpha equals 1 model to train a generative large language model for eliciting target emotions using reinforcement learning, with rewards provided by the coin alpha equals 1 model. Thank you for listening, and here is our selected bibliography.